All right, we're going to be working today on the EOC review packet that you received. We're going to go through and work at least 2 problems off of every page just to make sure that you know what you're doing. There are some example problems already worked out, but we're going to go ahead and work out 2 more. So we're going to start with the metrics and measurement, and we're going to do the first 2 problems. So the first problem says you start with 35 milliliters, and it wants us to go into deciliters. So we're going to start out, we have 35. Go ahead and make that neat. 35 milliliters. And we're going to deciliters. Okay, so this is a basic stoichiometry type problem or dimensional analysis. It's not stoichiometry because we're not changing chemicals. Okay, so I start with milliliters, and I don't want milliliters in my answer, so I get rid of it by putting it on the bottom. And if I have milli, I can go to the base, which is just going to be liters. And then when I go from liters, I can go into deciliters. So I go back over to the chart that they gave me, which we should pretty much have memorized for the basic ones. But it says milli stands for 0.001, which is 1,000. So there are 0.001 liters in every 1 milliliter. The milli means 0.001, so when I write this up here, it's the same type of thing. Okay? Now for deciliters, we go to the thing again, and deci is 0.1. So for every 1 deciliter, you have 0.1 liters. We're going to multiply straight across on the top, and we should get 0.35. Then we go to the bottom, multiply straight across, we should get 0.1. Deciliters is still on the top. 0.35 divided by 0.1, if I am not mistaken, is going to be 3.5 deciliters. All right, we're going to go and do another one. We're going to do number 4. 1,000 liters equals an unknown number of kiloliters. So we start with our given, which is 1,000 liters, and we're going to go to kiloliters. Now, liter is already a base, so I'm not going to have to do very much work here, but I want to get rid of liters because I don't want it as my answer. And from the other chart, it's going to say that there's 1,000 liters for every 1 kiloliter. So 1,000 divided by 1,000 is equal to 1 kiloliter. All right, that's the first page. Shouldn't have too many questions on that. We've been doing that since the beginning of the year. Next up is scientific notation, another one that's pretty easy, and they have examples worked out for you. But we're going to go ahead and do this. We start with 0.005. And 0.005, if we're going to write it in scientific notation, remember our goal is to have 1 non-zero digit to the left of the decimal. So my decimal has to move 1, 2, 3 places. And I will get 5 times 10. And since I moved my decimal to the right, I put a negative. And it'll be 3 places that I moved it. This is 5 times 10 to the negative 3rd power. Okay? Next thing I'm going to do is number 2. So my decimal isn't shown. It's actually right here. So I'm going to move it 1, 2, 3 places. This is 5.05 times 10 to the 3rd power. Now, another way that you can remember whether it's a positive or a negative exponent is if it's a small number, it's a negative exponent. If it's a big number, it's a positive exponent. 0.005 is a small number. It gets a negative exponent. 5,050 is a big number. It gets a positive exponent. Okay, so we're done with that page. You can come back and do it all yourself. Significant figures. So these ones we've been practicing for a while as well. They are actually pretty easy. It says determine the number of significant figures in the following numbers. So the first one we're going to start off with is number 1. Now, at first, you look at it and you might think that there are 2 significant figures because we have this right here. But we have to go back and look at our rules. And the rules that we have are right above it. They're also on your formula chart. And it says zeros between, not trailing, zeros in the beginning of a number, number 4, whose only function is to place the decimal point, are not significant. Example, 0.0025 has 2 significant figures. The way it says it on the formula chart, number 2, leading zeros are not significant. So if it comes at the beginning of the number before any significant digits, it's going to be insignificant. So the only one that's actually significant in here is the 2. So that is 1 significant figure. Okay? We're going to do number 7 next. And we want to count up the significant figures. So the 6 is significant. I know the 5 is significant. I know the 1 is significant. The questions I have are these 2 zeros and this 0. So I have to go back to my rules. And I like the rules on the formula chart because I think they're a little bit more concise. But it says non-zero digits and zeros between non-zero digits are always significant. So the non-zeros, that's the ones that we already highlighted on the top. And zeros between non-zeros are the ones that we're looking at now. So that means this 0 right here is also significant. Let's go back to our rules again. And it says zeros to the right of all non-zero digits are only significant if a decimal point is shown. So number 3 is saying that these zeros are significant only if a decimal point is shown. We have a decimal point, so both of those are significant. That means we have 1, 2, 3, 4, 5, 6 significant figures. All right, moving on to the next page. Percentage error. Now this is one we haven't used very often, but it's just a formula you plug in. You have an experimental value and an accepted value. You plug it into the formula. Okay? So the percent error is accepted value minus experimental value divided by accepted value times 100. Now those bars or brackets stand for absolute value. So all we're going to do is plug it in. The accepted value is 1.30 minus the experimental value, which was 1.24, divide it by 1.30, take the absolute value, meaning that you're always going to have a positive number, and multiply by 100. So I'm going to pull out my calculator, do this really quick. I have 1.30 minus 1.24. I get 0.06, divide that by 1.30. I get 0.0461538462. I'm going to multiply by 100. And I get 4.6153, and so on. If I look at my numbers, I started with 3 significant figures, so I'm going to round this to 4.62%. Pretty easy. It's just a formula. It's a plug and chug problem. Let's go ahead and do number 2. Our accepted value is 9.98 times 10 to the negative third. So we do 9.98 times 10 to the negative third minus our experimental, which is 1.24 times 10 to the negative second. We're going to divide that by 9.98 times 10 to the negative third. Absolute value multiplied by 100. This goes into the calculator again. We get 9.98 times 10 to the negative third minus 1.24 times 10 to the negative second divided by 9.98 times 10 to the negative third and then multiply by 100. And again, we started with 3 significant figures. So this time I'm going to get 24.2%. These are actually really easy. Like I said, they're just plug and chug problems. Next thing, matter and substances versus mixtures. So a matter is the basic building block of everything that you can touch. And we can break those up into substances, or we can break them up into mixtures. The difference between a substance and a mixture is that a substance, you can basically write the chemical formula. A mixture, you can't write the chemical formula, like salt and water. You put them in together, you have salt water, you have a solution of it, but you don't know how much of each thing is in every single little piece. So we're going to start with chlorine. Chlorine's going to be a substance. I know that because I can write its formula. It's Cl. The other thing that I know specifically about chlorine is it's on the periodic table. That means this is an element, which is why we call it the periodic table of the elements. All elements are on the periodic table. That, or we've given them names and they would go on the periodic table, but they're not common or undiscovered, so we don't actually have them. Okay? The next one is water. Now, water, we have to think, is it a substance or a mixture? I can write the formula for water. Formula for water is H2O. Now, this is more than one type of atom, so that means it has to be a compound. That's how we solve these problems. Okay. Go to physical versus chemical properties. Now, a physical property is one that can be observed without changing or destroying an object. A chemical property has to have a chemical reaction take place in order to observe it. So we're going to look at just a couple different things. The color blue. If you're just looking at a color, you're not looking at it changing colors. That's just a physical property. How about flammability? Can I know if something is flammable without first trying to catch it on fire? The answer is no. I have to combust it. That's a chemical property. Density. I can measure mass, I can measure volume, and I don't have to change the substance to do it. So that would be a physical property. I did an extra one on this one. These are pretty easy as well. Shouldn't take you too long. Next thing, physical versus chemical changes. So in a physical change, the original substance still exists. It's only changed form. A classic example is if we have liquid water turning into ice. It might look different, but it's still the same physical thing. It's still water. So if we can still have the same thing and we haven't chemically reacted with anything, we're going to still have the same substance. So first one is sodium hydroxide dissolves in water. Now, it didn't say that it reacted with the water, it just dissolved. If I wanted to, I can heat up the water, boil all the water out, and the sodium hydroxide will still be there. So it's going to actually be a physical change. Hydrochloric acid reacts with potassium hydroxide. There we go. Reacts is a big chemical word. That means that this has to be a chemical reaction. All right. Go on to the 8th page. Ideal gas law problem. All right, so to use the ideal gas law below, solve the following problems. Remember, ideal gas law is an equation of state. It's not talking about a gas as it changes. It's just what it is at that point. If I know pressure, if I know volume, the number of moles of gas, I can calculate temperature. If I'm missing any one of the variables, I can calculate from the other things. Okay, so the first one says, how many moles of oxygen will occupy a volume of 2.5 liters at 1.2 atmospheres and 25 degrees Celsius? Now, there's one important thing to remember. The temperature has to be in Kelvin. And on your formula chart, it gives us the formula. Where is it at? Gotta find it. There it is. Right behind that red line that I'm about to clear off, it says 0 degrees Celsius is equal to 273 Kelvin. A Celsius and a Kelvin are worth the same amount, but you start at a different value. So all I have to do to go from Celsius to Kelvin is add 273. So how many moles of oxygen will occupy a volume of 2.5 liters at 1.2 atmospheres, 25 degrees Celsius? I'm looking for moles. That's N. The pressure they gave me, 1.2 atmospheres. Times the volume, 2.5 liters. So I'm going to leave the units off. And that needs to equal the number of moles, which is N. I don't know what N is. R is the universal gas constant, or the ideal gas constant. And since we're using liters, atmospheres, moles, and Kelvin, I can just use 0.0821. And I can do 25 degrees Celsius is equal 25 plus 273 Kelvin. Okay? So now it's just a basic algebra problem. I'm going to divide the whole entire problem by 0.0821 because it's multiplying times the n. And I'm going to divide by 25 plus 273. So if I put this into my calculator exactly as I have it, I do 1.2 times 2.5. And I put a big parentheses around here. This will make everything good. I do 1.2 times 2.5 divided by big parentheses 0.0821 times, open up the parentheses again, 25 plus 273, close them down, and I get 0.1226 moles. Now all of this is done to two significant figures, so that's where I'm going to leave my answer. I should get 0.12 moles. Okay, it's really not so bad. It's a little bit of math, but you're not afraid of math. It's your friend. All right, number 2, it says, what volume will 2 moles of nitrogen occupy at 720 torr and 20 degrees Celsius? Oh no, it gave us torr instead of giving us atmospheres. What are we ever to do? Well, you could just change the torr into atmospheres, or you could be lazy like I'm going to be and use your formula chart. Because our formula chart gives us a couple extra things for our ideal gas constant. There's the good old 0.0821 from earlier, but, oh, it's actually not on here, I lied. All right, so we're going to have to change torr. And torr is not even on your formula chart. So that means we're going to have to look up torr. So, how about we use good old Google to help us out? Let's see. Convert. And we're going to say, how many torr was it? 720 torr. To ATM. Google will go ahead and do it for us and tell us that it's 0.947368421 atmospheres. Or since we only have two significant figures, 0.95 atmospheres is close enough. So my pressure is 0.95 ATM. My volume is unknown. Equals our number of moles, which is 2.0, times R, which was 0.0821, since we're using atmospheres again. And our temperature is 20 degrees Celsius, which is 20 plus 273 Kelvin. Solving for volume, we just need to divide the whole entire problem by 0.95. So we'll put it into our calculators again. 2 times 0.0821 times parentheses 20 plus 273 divided by 0.95, and we get 50.64, which will round up in this case to 51 liters. All right, so they threw us for a little bit of a loop with the torr, but we got it taken care of we know that we can transfer the torr that way, but let's go ahead and write this down. Let's see. 1 atmosphere to torr. 1 atmosphere is 760 torr. You'll probably need that later, considering there's more torr on this. So, if you're watching this video, 1 ATM equals 760 torr. Now, if I'm not mistaken, there's something else that's also 764. Oh, yeah. 1 atmosphere is 760 millimeters of mercury, and 1 torr is the same thing as a millimeter of mercury. Why? I really don't know. But that's your fun factoid for the day. All right, let's move on to the next piece. Atomic structure. The atom is made up of protons, neutrons, both found in the nucleus, and electrons in the surrounding electron cloud. Y'all know that. The atomic number is equal to the number of protons. The atomic mass is protons plus neutrons. Electrons are the same as the protons unless you have an ion, in which case everything changes. I have to take a break to take a... All right, I'm back. I know that didn't seem like very long to y'all, but it was about 5 minutes on my end. I had to take a phone call. All right, so we're looking at the atomic number of hydrogen. So, again, we go to our formula chart. It has on the very last page your periodic table, and it's turned sideways, which makes things more fun. But hydrogen, this number at the top right here, is the atomic number. So hydrogen has 1 proton. So we go back over into the chart. Hydrogen has an atomic number of 1. Atomic mass, that's at the bottom of the chart. We should be familiar with this one. It's 1.008. Mass number. What's the difference between atomic mass and mass number? I honestly don't know right now. So I guess I'm going to have to read some instructions. Oh, well, this one doesn't have a mass number. It's not what do we call those things? One day I'll remember what I'm trying to say right now. It's not an isotope. It didn't say hydrogen with a mass of something, like that carbon-12 that we see right here. Okay, so this is just going to be blank. Protons, well, it's atomic number 1. That's the same as the number of protons. The mass minus the protons gives you how many neutrons. 1 minus 1 is pretty close to 0, as far as I'm concerned. And the atomic number is the same number of electrons, unless you have an ion. So let's look at what an ion looks like. A hydrogen plus means that we took away an electron, but the atomic number is still the same. The atomic mass that you get off the periodic table is still the same. There's still no mass number on this one. You still have 1 proton. You still have no neutrons. But since I took away an electron to get a positive charge, I've got 0 electrons. Okay? So let's do one more just for good measure. Carbon is atomic number 6. I can look that up on the periodic table, or I can look at this little number right here and see 6. Its atomic mass from the periodic table is going to be 12.011. It's right there. That's going to be 12.011. The mass number is right here, and it's just 12. The protons would be 6 because the atomic number is 6. And the neutrons will be 12 minus 6, which is also 6. The electrons are the same number as the protons because it's not an ion. And you can go ahead and fill in the rest of those. It's going to be pretty easy. Not too much to do. Whew. All right, isotopes and average atomic mass. So whenever we're talking about isotopes of an element, there's usually a certain percentage that we see in nature, and we want to get them together, and we get the atomic mass, which is the one that you see on the periodic table. So all we have to do is add up the percentages. So our example is going to be number 1, and it's 80% iodine 127. So as a decimal, 80% is just 0.80 times 127. 17% iodine 126 is going to be 0.17 times 126. 3% iodine 128 is 0.03 times 128. And you just add them up. So you go ahead and you put them in your calculator, because that's the easiest way to multiply and add. 0.80 times 127 plus 0.17 times 126 plus 0.03 times 128, and we get 126.86. All right, that's pretty easy. How about number 2, 50% gold 197 and 50% gold 198? I think I already know what this is, but I'm going to go ahead and multiply anyway. So 50% is 0.50 times 197. 50% is 0.50 times 198. Put it in your calculator, 0.50 times 197 plus 0.50 times 198, and we get 197.5, which makes sense. It's the average of the two. And of course, this is atomic mass units. I always want to write our units down. So an atomic mass unit is the amount of mass for an atom, thusly the atomic mass unit. If I had a whole mole of this substance, all I have to do is change it from AMU to grams, because 1 mole is equal to the amount of atoms needed to change AMUs into grams. Okay, that's that one. Let's go on to the next one. All right, half-life of radioactive isotopes. Oh no, it's one we haven't done in class before, and they didn't give you examples, but it's really not that difficult. It's on your formula chart. So it says, how much of a 100-gram sample of gold 198 is left after 8.10 days if half-life is 2.70 days? So we're going to go to our nice little formula chart, and on the first page, it will say initial mass times 1/2 raised to the power of the number of half-lives is equal to the final mass. So get to that on your formula chart. It's right here. Initial mass times 1/2 raised to the number of half-lives is equal to our final mass. So we had 100 grams. That's 100.0, and that is our initial mass times 1/2 raised to the number of half-lives. So if the half-life is 2.7 days and I did 8.10 days, that's going to be 8.10 divided by 2.70. And that'll equal your final mass. So again, grab the handy-dandy calculator, and you do 100 times 1/2. I like to just use 0.5. Raised to the power. Now make sure to put this part in parentheses. 8.10 divided by 2.70. And we get a final mass of 12.5 grams. That's it. Next up, a 50-gram sample of nitrogen-16 decays to 12.5 grams in 14.4 seconds. What is its half-life? Okay, so we just do 50-gram sample. That's our final, or our initial mass, 50 grams. I'm going to go ahead and take the G out just because. And it says the We have the 1/2. And we need to know how many half-lives we get. Oh no, this one might be difficult. Okay, so I guess I need to define half-life for you. So half-life is the amount of time it takes for half of your sample to decay. So we're going to have to do this the old-fashioned way. We get 12.5 is equal to 50 times 1/2 raised to the n number of half-lives. The other way of looking at this is how many times do you have to multiply 50 times 1/2 to get 12.5? Okay, so we like to do it the easy way. Just do 50 times 1/2, and that gives you 25. And then you do 1/2 again, and that gives you 12.5. So that means 50 raised to the second power is equal to 12.5. Okay, so that's 2 half-lives. And we did 2 half-lives in 14.4 seconds. So 14.4 divided by 2 is equal to 7.2 seconds. All right, that one was a little tricksy. Let's see if we have any more that are tricksy like that. Let's see. That one tells you half-life. This one wants to know what is the half-life. So we're going to do the same type of thing. Just multiply by 1/2 until you get 62.5. Number 5, half-life. 250 grams left. How many grams were in the original sample? You're just working backwards. Shouldn't be too bad. If you have questions, feel free to send me an email. I'll still respond even though I'm on vacation with the seniors. Okay. Next is the periodic table worksheet. Where are the most active metals located? Well, our formula chart has a table on it. And it says activity series of metals in aqueous solutions. Well, lithium is the most active, followed by potassium, then barium, then calcium, then sodium. Let's see where lithium is. Well, lithium seems to be all the way over here in group 1. So does potassium, the top 2. So I'm going to guess that the most active metals are in group 1. And that makes sense. They're all the way over there, right next to group 18 going backwards. If you remove 1 electron, you look like group 18, so they really want to react. So where are the most active metals located? That would be 1. Where are the most active nonmetals located? Well, let's go by the fact that we said the ones that are closest to group 18 on the metal side would be the most active. So probably the ones closest to group 18 on the opposite side will be the most active nonmetals. That's group 17. Okay, and the rest are periodic trends. You should have that in your notes. Shouldn't be too difficult. Next up, ionic bonding. All right, pretty simple. All you have to do is start by drawing how many dots go around your things. So K has how many dots? K is in group 1, so K has 1 dot. Fluorine has how many dots? Well, it's in group 7A, so it's got 1, 2, 3, 4, 5, 6, 7 dots. So it looks like this K is going to go into there, and it's going to produce potassium fluoride. The potassium has a positive charge now, and the fluorine has a negative charge. Pretty simple. Let's try magnesium and iodine. So magnesium is in group 2, so it should have 2 dots. Iodine is in group 7A, which is 7 dots. Oh, so I can go ahead and throw this dot right in here. But that's not going to work all the way. I've got to have somewhere else for that other dot to go. So I get my buddy iodine over here, and that one goes there. That means this makes magnesium with a 2+ charge and iodine with a 1- charge, but you have 2 of them. That's how these work. All right, types of chemical bonds. All right, this is actually really easy. All you need to figure out is whether you have a metal and a nonmetal to be ionic, covalent, which is a nonmetal and a nonmetal, or if you have a mixture of both. Okay? So metals are on the left side of the periodic table, nonmetals are on the right. So if I've got a metal and a nonmetal, like calcium comes from group 2, chlorine comes from group 17, this one's a this one is a metal. That means this is ionic. Down here, if we look at this, this is a nonmetal. Hydrogen's weird because it can be a nonmetal or it could be a metal. So this is both. And this is a nonmetal. Now, it did say if you have a polyatomic ion, it would be ionic. But if you look at it the other way, it's all nonmetals, so this would have to be a both situation. If we look at carbon and oxygen, this is a nonmetal, this one's a nonmetal, this is covalent. Excuse me. Got a little bit of the sneezing. Shapes of molecules. All right, so you had a Vesper chart back in the day, which helped you after you get through everything. But let's go ahead and start by drawing a Lewis structure, because you need a Lewis structure to determine what kind of shape you're going to have. Unless, of course, you remember a couple little tricks. For instance, if you just have one element, or if you have 2 atoms, like this, the only way to connect atom 1 to atom 2 is with a straight line, which makes this linear. Again, same way. H, F, straight line. What about H2O, though? H2O is a little bit different. So we need to go through our steps to make a Lewis structure. First things first, we need to find out how many electrons we have. Let's see, we've got 2 hydrogens, or I guess the real first thing you need to do is draw the skeleton. We have 2 hydrogens, and each hydrogen has 1 electron. Because its atomic number is 1, it has 1 electron. And then we have plus 1 oxygen, and oxygen has 6 electrons. So 2 times 1 is 2, plus 1 times 6 makes 8 electrons. Next, we need to know how many pairs we have. So we do 8 divided by 2 equals 4 pairs. Then we're going to place our bonding pairs, 1, 2. So we did 2 bonding. So we start with 4 minus 2, means we have 2 pairs left. And those will go around our central atom. Okay? So let's see if I can find a Vesper sheet really quick. No. Got to go all the way down here and search for a second. Let's see. Instructional material. Vesper. Notes. Oh, look at that. A Vesper table. That's exactly what I was looking for. This is available on the website, by the way. I have it in the notes section. Okay, but we have two bonding pairs around this, or two structural pairs. That's where we start with. Two of those. Well, maybe not. Oh, we have four structural pairs. I'm sorry. Let's look. I have 1, 2, 3, 4. I guess I need a mouse cursor to be a little bit better. There's 1, there's 2, there's 3, there's 4. That's 4 total pairs. Now, 2 of those are bonded, and the other 2 are lone pairs, which means that this is going to be bent. And I actually knew that before I started because we know water is bent, right? And that's how you're going to solve these. Move on to the next piece. Now, there's also notes on that on the website, too. All right, mole and volume. For gases at STP, 1 mole occupies a volume of 22.4 liters. What volume will the following quantities of gases occupy at STP? Okay, so we have 1 mole of H2 gas. Well, we said 1 mole equals 22.4 liters. Dunzo. Now, the great thing is that is also on your formula chart. It says volume of ideal gas at STP equals 22.4 liters for every mole. So if I start with, how about 3.20 moles? Well, for every 1 mole, I have 22.4 liters. So now I just have to multiply. 3.2 times 22.4. I get 71.68. If I started with 3 significant figures, I get 71.7 liters. Pretty simple. All right, one that we haven't done before. Makes things real easy. Okay, determine the percentage composition of each of the compounds below. Okay, so this is going to be really, really hard in a not actually way. So, what we need to do is we're going to calculate the percent of mass that each of these elements has. So what we need to do is find out what the total mass is, and then we're going to do parts divided by whole. So the mass of a potassium from our periodic table is 39.098. So we start with 39.098. Okay. The mass of a manganese, not magnesium, manganese, is 54.938. And the mass of an oxygen is 15.999. But according to the formula I have 4 of those. So this is how I like to do this. I always set them up like this, up and down. And I'll get 39.098, 54.938, and 15, oops, sorry. I'm going to go ahead and put this in the calculator before I write it down. Do 15.999 times 4, that's 63.996. And I'm going to add them all up. So 63.996 plus 54.938 plus 39.098, I get 158.032. Now, what you know from your math classes is to get how much something is as a percent, you just take the part and divide it by the whole. So the part that is K is 39.098 divided by the whole, which is 158.053. So I do 39.098 divided by, it's 39.098 divided by 158.053, Then I get 0.247, which is 24.7%. Then I'm going to do 54.938 divided by 158.032, and I get 1053. Oh, no, it should be 0.032. So 39.098 divided by that. Okay, that one's still 24.7. This one is 54.938 divided by that. We get 34.8. And the last one, 63.996 divided by, and we get 40.5. All right, now the thing that you're supposed to do is check. And the way you can check is just add them all up to see if they make 100%. 24.7 plus 34.8 plus 40.5 is 100%. That's how we do those. I'm only going to do one because you don't have a lot to practice on. Well, I guess maybe I'll do one at the bottom. Okay. So what they're asking you to do at the bottom is do a percent composition and then multiply the amounts they gave you by that percent. So if we're doing number 8, how much silver can be produced from 125 grams of silver sulfide? We'll do Ag and S. Ag on the periodic table is 107.868. And we have 2 of those here. Sulfur is 32.066. Just one of those. So 107.868 times 2 is 215.736. And the other one is just 32.066. Add them up. And we get a total of 247.802 is our total. So if we want just this percent of silver, it's 215.736 divided by 247.802. 15.736 divided by 247.802, and we get 87.1% is silver. So we have 87.1% is silver, and all we're going to do is multiply that by the amount that we have, which is 125 grams. So 87.1% of 125 is just 0.871 times 125. We get 108.875, or let's just round it to 109 grams. So that's how many significant figures we have. And that should be that. And I've got yet another phone call to take, so I'll be right back. And we're back. Now we're going to be doing some balancing chemical equations, everyone's favorite. So the way I always balance is start by drawing a little box, because we can't change formulas, we can only change coefficients. And then I make an element inventory, so I've got nitrogen and I've got hydrogen. On the left I have 2 nitrogen, on the left I have 2 hydrogen. On the right I have 1 nitrogen and I have 3 hydrogen. Now, I remember something about if I see a 2 and a 3, there's a trick that I can do that I call the 2-3 trick, which means I'm going to put a 2 in front of the thing with the 3. So I'm going to put a 2 in front of this. And I'm going to put a 3 in front of the thing with the 2. So the thing that had a 2, I put a 3. Okay, and then I'm going to redo my numbers. I still have 2 nitrogens on the left, but now I have 6 hydrogen. And on the right, I have 2 times 1 nitrogen. That makes 2 nitrogen. And I have 2 times 3 hydrogen, which makes 6. 2 and 6 matches with 2 and 6. So my coefficients are 1, 3, and 2. Pretty easy. Let's go ahead and see if we can do one slightly more difficult. Let's do number 3. So on number 3, I make my element inventory. You know, you still have to box if necessary to make sure you don't change anything. Okay, so I'm going to have Na, I'm going to have Cl, I'm going to have F. On the left side, I have 1 Na, 1 Cl, and 2 Fs. On the right, I have 1 Na, I have 1 F, and I have 2 Cl. Okay, so I just go top to bottom. My NAs are balanced 1 and 1. My CLs are not. So I need to put a 2 in front of the CL on the left. So I put 2 there. And that changes the number of CLs I have to 2. But it also changes the number of NAs that I have to 2 as well. So that means I got to start over at the top. So now my 2 doesn't match with my 1. So that means I need to do 1 times what number gives me 2. That's 2. I need to put that in front of the NAs on the right. When I do that, it changes my number of NAs to 2. And it also changes my number of Fs to 2. And look at that. Balanced on both sides. Very good. So the coefficients will be 2, 1, 2, 1. Balancing chemical equations is actually pretty easy. Just make sure you follow the steps, and you'll be right every time. All right. How about now we get a little bit more fun. We're going to write out the chemical equation. So we need to know what zinc is. Go to our periodic table. Zinc is Zn plus lead 2 nitrate. Now, that 2 really helps us out because it means that we know that this is lead with a charge of 2. And then we have nitrate, which is on our periodic table or our formula chart. It's listed as NO3, and it has a charge of -1. So what I need to do is crisscross my charges. That means this 1 comes down here to the lead. Remember, it's an invisible 1 now. This 2 needs to come out to the other side of the 3, and I need to put the NO3 in parentheses. It means I have 2 nitrates to balance out the charge. Okay? And it yields, that means put an arrow, zinc nitrate. So again, we have Zn for zinc, and this time it's nitrate. NO3, remember nitrate still has a charge of -1, plus lead by itself. Now we need to know what is the charge of zinc. So I'm going to actually break out the periodic table and look at it. Oh, there's a trick I told you. Remember aluminum, if we're looking, that is the 3rd stair step. Zinc is the 2nd. Silver is the 1st. Zinc has a charge of 2 plus. Aluminum has a charge of 3 plus. Silver has a charge of 1 plus. 3, 2, 1, 1, 2, 3. So that means when I come back over here, I need to write the charge above my zinc, and it is also 2, which means if I crisscross, I'm going to get the same type of thing going on. 2 and 1, and we're good. Now all we need to do is balance. So I'm going to make my element inventory. I've got zinc, I have lead, and I'm going to keep the nitrate together because I've got nitrate on both sides. Okay. On the left, I have 1 zinc, I have 1 lead, and I have 2 nitrates. On the right, I have, look at that, 1 zinc, 1 lead, and 2 nitrates. We're balanced. All 1s. Okay. So let's do number 2. We have aluminum bromide. That means we have aluminum. And if you remember from just 1 second ago, aluminum has a charge of 3, because it's that top step, the 3rd step. And we have bromine. Now, bromine, I know its charge because it's on the periodic table. Bromine is in group 17. Now, group 17 is one step away from group 18. If I'm one step away from group 18, my charge is going to be 1. So I come back over, and my charge for bromine is 1. So crisscross, the 3 comes down to the bromine, and I put the invisible 1 next to the aluminum. Okay? Plus chlorine. Now, chlorine's an interesting little devil because it's part of the Brinkelhoffs. Now, what's interesting about Brinkelhoffs is that they exist as diatoms, or diatoms, or diatomic, meaning that if you just have chlorine all by itself, not bonded to anything, it'll bond to itself, like that. Okay? And they yield aluminum chloride, so we have Al with a 3 charge, and Cl. Cl is also in group 17, which means it has a -1 charge. So crisscross, invisible 1 goes next to the aluminum, 3 goes next to the chlorine, plus bromine. Now again, bromine is part of the Brinkelhoffs, which means when bromine is all by itself, not bonded to anything else, it'll be Br2. Okay, now we just need to balance. We've got aluminum, we've got bromine, and we have chlorine. So there's 1 aluminum on each side. There are 3 bromines on the left, 2 bromines on the right. There are 2 chlorines on the left, 3 chlorines on the right. Looks like a good time for the 2-3 trick again. So what I'm going to do is actually do this twice, I think. But the thing with the 3, I'm going to put a 2. The thing with the 2, I'm going to put a 3. So for the bromine right here, it has a 3 on the left. I'm going to put a 2 in front. For the bromine on the right, I'm going to put a 3 in front. For the chlorine on the left, it has a 2, so I'm going to put a 3. And for the chlorine on the right, it has a 3, so I'm going to put a 2. And I'm going to do all my numbers again. So now I have 2 times 1 making 2 aluminums on the left. And I have that 2 also makes 6 bromines. And then the 3 times 2 for the chlorine makes 6. On the right side, I have 2 times 1 giving me 2 aluminums. I have 3 times 2 chlorines giving me 6 chlorines. And 3 times 2 bromines giving me 6. Matched up. We're good. All right. Moving on. Maybe. There we go. Almost to the last examples. Write the expression for the equilibrium constant for the reactions below. Okay, this is another one that we haven't really done in class, but it's on your formula chart, so that's what we're going to do. Your formula chart at the very front has something that says equilibrium constant for little a, big A, plus little b, big B, arrows, little c, little d, big D. So the equilibrium constant, the KEQ, is equal to capital C raised to the C power, capital D raised to the D power, over A to the A, B to the B. It's actually really simple. So what we're going to do is use that. So the A's and the B's are our reactants. Okay? So I have N2 raised to the first power, because there's an invisible 1 right here. I'm going to have H2 raised to the third power. That's the 3. That's the bottom. That's the A and the B. Now I don't have a C and a D, I just have a C this time. So I'm going to have NH3 raised to the second power. Pretty simple. I'll do the second one. On the bottom we have KClO3 raised to the second power. And on the top we'll have KCl raised to the second, O2 raised to the third. Now these ones are important because it asks you for these on the next page. So what I'm going to do real quick is just copy what I've got, because I'm going to need to look at it. Go ahead and clear off all the ink. Now you should all have this on the next page, but it's going to give you what your constants are now. So the constants it's going to give us, I know that this is going to get small, but you have it on your page, is 0.0100 for NH3. So I'm going to start by putting 0.0100, and I'm going to raise it to the second power, divided by, on the bottom, it has N2, which is 0.0200, and I'm going to raise that to the first power, times 0.0200, and I'm going to raise that one to the third power. So I just put it into my calculator just like that. Make sure to put big parentheses around the bottom when we do this division so that we don't mess up in the calculator. So 0.0100 raised to the second power divided by, and I open up a parenthesis right here. I'll put 0.0200 raised to the first power times 0.0200 raised to the third power. Close off my parentheses. And I get 625. Okay, now I'm going to do the next one. Where am I? Looks like I only have one constant, so that means I just have to do one thing. Put the 0.0500 in. And I'm going to raise that to the third power. I get 1.25 times 10. And that's about it. Not too difficult yet again. Okay. Oops. Gotta put my green marker down before I try to scroll up the page. Go on to the next piece. pH and POH, everyone's favorite. This is the last page. It's been fun, but we're almost done. Okay. So we know how all of the pH and the POH works. We've done lots of these things, but we'll go ahead and do it all again. So let's begin. If I have a pH of 7, I know pH plus POH has to equal 14. So 7 plus what number makes 14? That's right, 7. If I have a pH of 7, or I have a pH of 7, am I acidic or basic? And it's right in the middle, so that means it's neutral, or neither. Okay? Now for the fun part. Remember, pH is on a log scale, so we have to use opposite log to get what the H plus and the OH minus are. So the opposite log is on the same button as the log, except you hit second. So we hit second log, which will give us opposite log, and it looks like 10 raised to the power. So 10 raised to the power in this case of 7. That's my H plus. But it's a negative. And it's the same thing for OH. 10 raised to the negative 7. That's it. All right, let's go for the next one. So we have the OH concentration this time, and our formula up there says pH is negative, or POH is negative log of OH. So I just go into my calculator, I hit the negative, then I hit log, and I put 10 raised to the negative 4th. And what I'll get for my POH is 3. I know pH plus POH equals 14, so 11 plus 3 makes 14. And now all I have to do is work the other way for this one. So if my pH is 11, I hit the opposite log button, and I put in negative 11. So that would be 10 to the negative 11. Yes, I should be putting molar. And so if pH is greater than 7, we have a base. That's pretty much how these work. That's the last one. Good luck. If you have any questions, feel free to email me. You can look at all the tutorials that we've done through the year. You can search on YouTube or the Googles. There's always a tutorial available. And this should help you a lot as you study for your end of course exams. Y'all have a good week.